So last part here, the Poisson distribution. Here is the type of story that's going to yield a Poisson distribution, Poisson probability distribution. First of all, this is still a discrete random variable. Just get this set up here. Meaning that the numbers that we're looking at, our random variable will only have discrete values. We shouldn't be getting decimals for x. Let's take a look at what x could represent. A Poisson experiment says that there is a fixed interval of time or space. So we set up in advance, we could say it's this space or this time, or it might be a space and time simultaneously. We are observing the number of events that occur in that time or space. The events happen at a known average rate mu. The likelihood of an event occurring is independent of the amount of time or space since the last event. Now, I've done problems where we're counting the number of hurricanes occurring in the Atlantic during a given year. This one's a little less dramatic. But we are going to be counting the number of events in the interval. So the random variable x is how many events are occurring in the interval. The possible values of x are 0, 1, 2, ... but there's no maximum value of x. Sorry. We provide a portion of the table, but the table is infinite. Like if we thought about hurricanes, we do know that it's unlikely we will have 1,000 hurricanes in 1 year. That's pretty unlikely. But could you state definitively that there will be no more than 12 hurricanes, or no more than 13 hurricanes, or no more than 14 hurricanes? The probabilities will get lower and lower, but they never hit 0. So that's why our table is actually infinite. We will say that x has a Poisson distribution. So we say x, and then we put a squiggle for the distribution. Big P for Poisson, not a B for binomial. And then we put that parameter mu in the parentheses. There's only one parameter, and it is mu, although some textbooks call that parameter lambda. So you might see a lambda somewhere, but we typically call it mu. Mu is the parameter of the distribution, the known average number of events in the interval of time and space. So my example is that I'm sitting in the STEM learning zone for 1 hour. This is my time and my space. The STEM learning zone, based on past experience, I expect to have 5 students on average come and ask me questions during that time. So let my random variable x be the number of students who come to the STEM learning zone during my 1 hour shift. X is distributed Poisson 5. Now I do need to state the time and space when I define my variable, but in terms of my parameter, all I have to give the calculator is the 5. Then I can go into the calculator and use Poisson PDF to generate all of these decimals. And notice that my table goes from 0 up to 10, and then I have a ... because conceivably 11 students could show up. So second distribution, arrow down until we get Poisson, and I'm going to use Poisson PDF. Mu is 5, and first of all I'm going to type in x equals 0 and paste it. And my calculator is still set to round to 2 decimal places, so that's going to be pretty handy. Second entry brings back the previous entry, and I can just keep repeating myself. And you can see that we're generating these values for our table. Those are all probabilities, so they're all between 0 and 1. And if I wanted to, I could go to second distribution, scroll down to Poisson PDF, enter, put in 5, don't put anything in for x. Huh, it's not letting me do that. Oh, I get it. Because the Poisson table is infinite, it won't let me not specify the x value because it can't spit out all of the answers the way the binomial would. So I am stuck giving it answers. So I'll just check one more. I'll say 6, and it should return 0.15. Sure enough, there it is. So the probability of 6 students showing up is 0.15. The highest likelihood is to get 4 or 5 students. It's kind of funny because I would have expected 5 to be the highest probability, but the probability of having 4 students was actually the same as 5 students. Now if I change my mode back to float, I'm curious. Second entry, let me do the 4. And then second entry, let me do the 5 one. Oh, they're exactly the same. I'm surprised. I really thought this would be the highest probability right here. Yeah, so we do not calculate these with our brains. We calculate these from the calculator. And after that, I can just ask you questions like find the probability that x is 7, find the probability that x is less than or equal to 7. And I feel like all of these are pretty easy once you've generated the table. What is the probability that x is greater than 7? Greater than 7 would only be these, well, it wouldn't only be these 3. It would be all of these, and that's where it gets a little tricky. You might be like, oh, 7 and 4 and 2, that's just going to be 0.13. And it's close to 0.13, but it's a teeny bit higher because we have more values. This table goes forever. So that's when you start to find the usefulness of saying that probability of x greater than 7, see how I started it at 8? The probability x greater than 7 is 1 minus the probability of x less than or equal to 7. So this is the probability that x is less than or equal to 7. And I get that by going second distribution, Poisson CDF, mu is 5, 7 or lower, enter. It gives me 0.8666 for 7 or below, so I do 1 minus second answer, and I get 0.1334 if I round it. So there's only about a 13% chance that more than 7 students will show up. Okay, so yeah, letter D is very similar. And I do find that these are trickier, these are easier. So pay special attention to these. Let me know if you get stuck.